All right, so I may start. And the title that Giacomo gave is slightly changed on my slides, but it covers exactly the same subject. And the work I will be presenting now is a work that I've been doing over the last 10 years. So I will present just part of it. And it's a large project, but I'm undergoing project with Nicolas Gast from INRIA in Grenoble as well, and Jean-Yves Le Boudec from EPFL and many others have really contributed to this. But the things I will be showing here is mainly the work based on our common work. So the context of the work is when, you may know that when you deal with very large Markovian systems, then you're often hit by what is called the curse of dimensionality, meaning that if you have many objects composing your system, the state space of the Markov chain grows exponentially with the number of objects. And therefore, you cannot really solve anything formally in that case when the number of objects composing your Markov chain or your Markov decision process is large. By the way, I'm just thinking out loud about this. So if you have any question, please do not hesitate to interrupt me. I'll try to answer the questions online. It will be more lively because seminars on Zoom are a little bit talking in the void. So please don't hesitate to interrupt the talk if there is anything you don't get. Okay, so an alternative approach to deal with a large problem is to actually build an even larger problem and let the number of objects n go to infinity. And surprisingly, when n goes to infinity, then things become easier when n is small or smaller, large but not infinite. And so I will show you exactly how it works here, and I will show you how to build this asymptotic model even without the usual Lipschitz condition. I will be talking a little bit about this a little later, and also I will show you how this approach can be used for optimization, when the limit, when n goes to infinity, commutes with taking the sum. So some applications of this work that I've been doing over the past 10 years, as I said. So we have been looking at how it can be used to actually evaluate the performance of work-stealing systems. I will talk a little bit about this in the following. How it can be used to establish proofs of optimality of some policies. For example, the optimal worm infection strategy that I will be also mentioning later. It helps us to prove qualitative results, for example, show the stability of some strategies in some cases, design new control policies, for example, for the brokering of parallel systems, and also how you can actually extend this approach to deal with absorbing states. This I will not be talking about it. Improve speed of convergence. This I will not be talking today about it either, but I can send you some references if you're interested, and how it can be extended to cases which are heterogeneous. But this also will not be covered by my talk today. Okay, so let's start. So the main idea of this approach is to use what is called the mean field approximation. I don't know if you're familiar with this approach, but I will explain it a little bit in the rest. So the mean field approximation is the first changing the state space from the state of each object to the empirical measure, define the drift and the scaling, and then prove some convergence results. Now we'll cover some applications where I'll show about the power of this approach, and we'll apply it to a push-pull system, which is a partially centralized, decentralized system in queues. And finally, but last but not least, I'll show you how it's used for optimal control, and how you can define optimal mean field and the central limit theorem for those. Okay. So a mean field approximation studies a large system where you have a combinatorial explosion of the number of states. So imagine you have a large discrete event dynamic system made of n objects. And each object has a state space, a finite state space S. So when you look at the state space of the whole system, it's S to the n. And the system has a random behavior. Oops. And when you go to the limit, then you will construct, instead of this large discrete event dynamic system, a continuous dynamic system, which will be living over the unit simplex in dimension S and not over S to the n, and have a deterministic behavior. And to construct this, you need two ingredients. First, we have to define the empirical measure, and you have to define the drift. So let's do the construction for a Markov model. So imagine you have n objects, O1 and On. And O1 of t is a state of object 1 at time t. And you assume that the collection of the n objects forms a Markov chain over time. Let's say for now that it's in discrete time, but it could also be in continuous time. And you assume, what is important here, that the dynamics of the system is invariant under any permutation of the objects, which means that if I exchange O1 and O2, I have exactly the same dynamics, meaning that the dynamics depends only on the state of the objects, but not on their identity. There is nothing like the first object. There is nothing like the second object. It's just that you have n objects, one of them being state O1 of t, one of them being state O2 of t, one of them being state On of t. Is it clear? I mean, objects can be exchanged without any change in the dynamics. And once you have this important assumption, you can define the empirical measure. And the empirical measure is, I called it M here. So M of t is, at time t, is a proportion of objects in state On of t. Okay, so you have a finite number of possible states for all the objects, and Mn of t counts how many of them are in a given state, and how many of them are in another state, and so forth. And under the assumption that the dynamics is invariant on the permutations, then Mn of t is also a Markov chain. So that will be important. So the empirical measure also follows the Markov chain dynamics when the objects are exchangeable. And since Mn of t is a Markov chain, you can define the drift of the Markov chain. The drift of the Markov chain in state M is expected change of a one-time step. So the drift under state M, small m, is the expected change between time k and time k plus 1, as written here. And so that's a drift, the classical drift of a Markov chain. And here we will let n go to infinity. And when n goes to infinity, that drift dn will actually grow or at some rate that is given by epsilon n. So epsilon n is the order at which the drift grows with n. And so we will actually define the scaled drift as f, which is d over epsilon. Basically, in most cases, the drift actually scales as n. So in most cases, epsilon n is just n. But there are cases where it's not. So actually, all of this works for any kind of limit behavior of the drift. Okay. Let me give you a simple example of how to define the empirical measure. This is example taken from this work stealing dynamics that I was talking before. So it's a very elegant and very efficient way to do load balancing in a system where you have actually no a priori idea of the way that the work is balanced between the processors. So imagine you have like here big N processors, and each of them has a buffer in which the workload of the processor is stored. So here, for example, processor 1 has 4 pending jobs to be executed. Okay. So here I have, how many do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I have 13 processors, and each of them has a state. So the vector that is given below actually is the state of all the processors. And what work ceiling does, so when the process, like processor here, processor number 12 is idle, it has no work to do. And when the processor is idle, then it may still work from other processors. So the dynamics is the following. The idle processor chooses at random one of the processors with the highest load. Here you have two of them. You have two processors with load 5. So the idle processor chooses one of them and steals from it half of its work. So here you jump in this particular state. So here you cannot split 5 by 2. So it steals 2 jobs from the heaviest loaded processor. Okay? And at the same time, you have, of course, stealing, but you have also jobs arriving in all processors using some random Poisson arrival rate. And you have also service at all the processors with some given rate. Okay? And so here have written the change of state from the initial state to the state that you get after the steal. But now let's look at what happens for the empirical measure. So you agree with me that when the number of processors grows, the state space also grows. So there is no way you can scale using the classical state space. But instead, we look at the empirical measure. The empirical measure here is just how many processors have 0 jobs in the list before, how many processors have 1 job, and so forth. So my empirical measure here is given by this stack here that gives you the number, the measure of the initial state. And after the steal, you see that the number of processors with 0 jobs decreased by 1. The number of processors with 5 jobs decreases by 1. The number of processors with 3 jobs grows by 1. And the number of processors with 2 jobs grows by 1. And this is exactly what happens when you go from this state to that state. And now I will look at the drift in this Markov chain instead of looking at the drift in this one. Okay, I will see how this one changes over time in expectation. Is it clear? So, okay, I look at the drift over time, Mn of t, and here I have plotted the proportion of idle processors with respect to the proportion of processors of type 2 with 2 jobs. And this is how things change over time. Okay, this is the trajectory of Mn of t starting from here, and this is how it changes over time when n equals 10. So I have taken a sample trajectory with 10 different processors. Now, if I increase number of processors, I go from 10 to 50, and this is how Mn of t changes in the scaled time. So time is scaled by this scaling factor epsilon. And this is how the trajectory looks like. And now let me go to n equals 1000. And the 1000 trajectory is actually given by the red curve that you see here, while M of t is a deterministic trajectory just following the drift, the function f. And you see that as n goes to infinity, the red trajectory gets closer and closer to the deterministic system M of t that I will define later, and it gets more and more deterministic when n goes to infinity. So the scaled trajectories converge to a deterministic curve. And this deterministic curve is given by the drift, which is not denoted here f bar. I will explain what f bar is. It's a scaled drift. I just defined it before. So let me go to the equation at the top. So when I look at the expected, at the change of, the dynamical change of m over time, it follows the expected behavior f plus the random behavior of n, which is here written as a noise. And when n goes to infinity, this converges to the solution of some differential system m equals f of m of t. And not actually, it will not be a differential equation, it will be a differential inclusion, because you will see that f here may not be differentiable. So this is what I do here. And this is what happens when you hit the border in the previous example. In the previous example, you have a drift that goes from that goes up for the x2 coordinate and down for the x1 coordinate. But then after some time, you hit, after some finite time for the deterministic system, you hit the border where the number of idle processors equals 0. And when the number of idle processors equals 0, then the drift suddenly changes to, the expected drift changes to this line here. And so you see the drift in this system is not differentiable. So you cannot define a differentiable solution to the deterministic system. So this is a classical way to solve this kind of problem. So instead of looking at the drift, you look at what I read right here. I convexify the drift in the points where it's not uniquely defined. So in point when the x1 here equals 0, when the q1 is empty, then the drift actually is not defined as either the drift in the positive half plane or the drift of the vertical line, but as a convexification of all possible points in this set. So now the drift is not some value, but it's a set. It's a set of all the possible values between the extreme ones here. Okay. And when you do that, you can define actually the convexified drift as follows, which is defined in all cases. So you look at the drift with n objects at a point yn, where you let yn go to m, the point where you want to define the drift, and you look at all the accumulation points of these quantities, and then you take the convexified set, the convexification of all these points. And this defines the drift in point m. So now f of m is a set, okay? The convexified set of all the accumulation points of the drift around point m when n goes to infinity. And now you define the differential inclusion dm belongs to f of m with initial condition m of 0 equals m0, the initial condition for the empirical measure. And you have the following theorem, but actually can be proven, sorry. So if when n goes to infinity, there is a technical condition on the drift, which is a small one here, but it cannot grow too fast in m. But otherwise, as soon as the initial condition when n goes to infinity converges in probability to the point m0, then your system n of t, your stochastic system, uniformly in t, so we take the sup for t between 0 and big T, approaches the solution of the differential inclusion when n goes to infinity, actually in probability. And this is true for all t. Here, m is all the possible solutions of the differential inclusion. So now, a corollary of this theorem, which is actually a more effective way to look at it, is when the differential inclusion has a unique solution, which is called m, then you have that mn converges to m in probability. So this actually establishes this mean field approximation of big M as a solution of a differential inclusion. So the early work on mean field approximations used the fact that the drift had to be Lipschitz. And so here we show that actually we don't need that the drift is Lipschitz to have a solution of the system. But actually, when the drift is not Lipschitz, you need a unique solution to the differential inclusion to have a real nice property. Otherwise, the property here is not as good because you have to take one trajectory, a good one, in the set of the solutions. So let me comment a little bit on this result. So this theorem has good points and also drawbacks. So among the positive points, we have the fact that you have a constructive limit of your system. It's a completely general convergence result. There is no requirement about the convergence of the drift, and it holds for all drifts. But on the other hand, no uniqueness of the solution in general, and the speed at which you have convergence is not given and could be as slow as you want. So we can construct examples where the convergence rate to the mean field limit is as slow as you want. However, if you have some kind of Lipschitz condition on your differential inclusion, which is given here, that you have some kind of L Lipschitz condition on F, then you can give actually some convergence rate to the limit. Let me give just a very, very fast check of the proof. And we use the stochastic approximation method to prove it. So this is, I mean, there are other ways for example, propagation of chaos to prove these kind of things, but here is the case where we don't look at the trajectory, but only at what happens at time t. So we can use the stochastic approximation method. So you can see M as something that evolves, like I just said before, like M at time k plus 1 is M times k plus the small change epsilon n times the drift plus noise, and this noise has is actually a difference of martingales and has expected conditional expectation with respect to the past, which is 0. And so when you look at what happens after k steps, you can sum, and you have this kind of equation. And so you recognize the first part is just a discrete approximation of the differential inclusion, and the other part is some noise. And this noise actually will converge to 0 when epsilon n goes to infinity, goes to 0, because epsilon n actually is 1 over n. So this quantity here will go to 0 because the sum of the noise basically grows as square root of n, let's say, and epsilon n grows to 0 with rate 1 over n, and so this quantity here will go to 0. So this is basically the idea of the proof, and it's actually how stochastic approximation is done. So let me try to give you some examples of how you can use these results in some concrete cases. So let's say that I use the following one. So you have two queues, Q1 and Q2, and you have one server that has rate 3. And I look at the fluid approximation of this queue. So I start with a very, very large number of n. Here is the number of customers in the system, the n that scales. I let n go to infinity, and I will look how this actually behaves with time. And here I say that Q1 has full priority, meaning that when Q1 is not empty, the server always serves first Q1. And the server will only serve Q2 when Q1 is empty. And we want to look at what happens over time. Well, actually, this is a very similar example to what I did with work stealing. So the size of Q1 and size of Q2 here are given. This is the drift. Okay, the drift is when in expectation, when the Q1 is not empty, then it will decrease by 2 units of time on average, because your rate is 3 and the other rate 1, so it decreases by 2. And the Q2 actually grows by 1 because it's not served. So when Q1 is not empty, this is the expected drift of your system. However, when Q1 is empty, of course, Q1 will grow with rate 1, and Q2 will decrease with rate 2, because the server will actually serve rate Q2. But this is only when Q1 is empty. And so they typically have a drift which is not differentiable, neither continuous around the vertical axis here. So we can play the game before, we do convexification, and we can compute the solution of your system, which is unique here and which is given by this red line. So this is how the limit of the system behaves when the number of customers grow to infinity. And this is actually a very nice way to prove that this is actually the behavior of the system. Here, the differential inclusion has a unique solution, and you can actually prove that this is the way the system behaves over a large number of customers. Let me give you another example of using this theorem, slightly more convincing, which is the following. So here we have a server farm. So you have many processors, and all these processors, they serve, packets, and the packets are actually completely distributed among the processors. So you have a rate lambda arriving in Q1, rate lambda arriving in Q2, and so forth. And you have a large number of queues. This is a server farm. But this system here is a little bit inefficient because due to randomness, at any point in time, you will have some servers which are idle and some other servers which will be very loaded. And so you want to add a little bit of centralized decisions to this very distributed system. So here it's completely distributed. Let me add some little bit of centralized decision. So here I add a queue, an additional queue here. And so since I want to keep the total computing power equal, so I decrease a little bit the computing power of all the processors. Now they all have a service rate 1 minus p, all of them. So p is a small number, okay? And I add one queue whose serving speed is n times p. So you see that the sum remains equal to n. The global service speed is still n. And this queue here is centralized. So it has a very small processing capacity. Let's say p is very small, but it can serve packets in all the queues. So it can help the other guys. And it helps them by serving at each point in time the queue with the largest queue. So here the decision and the policy, the scheduling policy of this processor is to serve at each point in time the largest queue length. So it looks at the largest queue and it serves it first. This is for largest queue first, okay? And I also add some partial brokering. So the packets now, they arrive at rate 1 minus q times lambda. And there is some smart brokering processor that has just a partial arrival stream, n times q times lambda. And this one sends packet in a smart way by using the policy join the shortest queue. So the packets blindly arrive in all their assigned processors, except for a small portion of them that actually are smartly brokered to the least loaded system. So you have two kinds of centralized systems, one on the server side and one on the arrival side. And you want to actually try to see what happens when the number of processors here grow to infinity in this system. So this, I will not detail this, but this is the drift. This equation here, the blue one, is actually the differential inclusion. It's a differential inclusion here because the terms ui and vi are either 0 or 1, depending on whether the qi is the least loaded one or the highest loaded one. So depending on that, you have terms ui which are either 0 or 1 here. And this differential inclusion here, we can show that it has a unique solution, and that the unique rest point fs equals 0 is a global attractor of all trajectories. I didn't speak about that because so far I spoke only about finite time, but also this is also valid in infinite time horizon. And this is what happens. So let me explain. This curve that I show now are not simulations. They are the solutions of the differential equations. Okay, so they are the approximate behavior of the system when n is very large. So here, this is how it works without any help or brokering. So completely decentralized system. So this is the system load here. When the system load goes to 1, of course, the average response time of the packet goes to infinity. And this is how it evolves over time. This is a simple MM1 queue. And here I plotted the queue length probability. So this is a probability, but the queue length exceeds L as a function of L. Here, the load is fixed to 0.98. So I fixed the load to a high number, and I look how the distribution of the queues grow with L. So this is, of course, the probability that the queue length is larger than L in the system. And now let me add some coordination. So first, let me add a helper in the service. So here I add one server that can actually help those servers with a very high load. And you see that the average response time is much better. Okay. But what is more remarkable is about the queue length. And the queue length, the probability that the queue length exceeds 40 is 0 now. So in the limit, no queues will have more than 40 packets in their queue. The probability that you exceed 40 is 0, absolutely 0 in the limit. So you see the helper is a really nice way to bound the queue length in the buffers. And now I add a broker. If I add a broker, then although the queue lengths still grow to infinity, they are much better, of course, than without any broker. But the broker has a remarkable property in terms of average response time. And you see that even though for the broker, when you add a broker, the load is 1, the average response time remains finite everywhere from 0 to 1 in the limit. So the broker helps in the average response time, while the helper helps for the queue length. And of course, if you add them both, you win on both sides. If you add both a helper and a broker, then you have a finite average response time and a finite queue length. So you see, this is a way to dimension your systems in a very nice way when you have a very large, let's say, cloud computing problem. Adding a little bit of centralization helps a lot in those cases. Okay, I'm done with the examples that I wanted to show for the performance evaluation side. And now I will move to the optimal control case. So here I will assume that I have the same as before. I have a Markov chain with many objects which are exchangeable, but I add in my transition matrix actions. So now a controller may act on the system, and now the probability to move from state I to J depends on the action taken by the controller at time t. So here my kernel K depends both on the initial and final state, but also on the action taken by the controller. So the controller takes actions. The set of action is called A. And the policy is a way to assign to each state which action to take. So if I am in state I, and I apply policy PT of I, which gives an action, it will change the probability to move to the next state J. This is a typical Markov decision process framework. And at time t, I have a cost of my system, which is called C of M of t. So it's exactly a Markov decision process, but for the empirical measure. So I assume that the empirical measure is controlled by some actions. And the goal of my controller is to minimize the cost over time. So I look at the sum of the cost of some policy pi. So here notation gets heavy, but you have to follow me. So C is a cost, pi is a policy used by the system, m pi of t is the empirical measure at time t under policy pi. C is the cost, so I sum the cost from 0 to t, and I take the expected value of this, and I call this V pi. So V pi is the cost starting from M0 of a policy pi. Okay? And I want to minimize this, so I call pi star the policy that minimizes the cost. So pi star achieves the infimum of all possible policies of this expected value. So I will call this V star. V star will be the minimal cost of my system, and it corresponds to the value of the optimal policy pi star. And of course, everything here is given for a finite n, for a finite number of objects. Is it okay? So this is the classical way to define a finite horizon Markov decision process, this time over the empirical measure. And now I look at the limit. I go at the limit when n goes to infinity. So at the limit when n goes to infinity, there is nothing like a policy that gives the actions, because everything is deterministic. So now the action is given by an action function a of t. So a of t is the action taken at time t by my system. Of course, the drift now becomes f of a. So the drift becomes the drift at time t depends on the state empirical measure and on the action taken. Okay, I have the same scaling as before, epsilon n. And I look at what happens for the MAT. So MAT now is a deterministic limit of my system under action function A. So this is what happens. So it becomes a deterministic inclusion where the derivative of MA belongs to f of MAA. Okay. I have a cost which is just the integral of the cost over time under policy A. And I want to define V star of M0, which is infimum cost of all possible action functions. So this is the definition of the cost under the deterministic limit for a given action function A of t. So on one side, I defined what happens for the finite number of object system, the one that actually follows the random behavior given by this kernel here. And here I define a controlled system in continuous time under a controlled action A, deterministic. And this is what happens. So I want to compare the optimal stochastic cost V star n and the deterministic cost V star given by the controlled deterministic system. And here is the theorem. So these are the positive points and negative points. Positive points. First of all, the values converge. So when n goes to infinity, the optimal value of my finite system n converges to the value of the deterministic system. Furthermore, if I look at the optimal action function A star in the deterministic system, and I apply this deterministic function in my stochastic system, I got this is a cost of using A star in my stochastic system. And if I look at its value, it will also converge to 0 when n goes to infinity, meaning that the policy A star becomes asymptotically optimal when n goes to infinity. And this is remarkable because A star actually is a blind policy. A star does not even look at the current state of my system. A star just says which action to take at time t, blindly, without even looking at the current state. And this shows here that such a policy can be optimal when the number of objects grows to infinity. Meaning that, open loop control becomes as good as closed loop control when the number of objects in your system grows. But we have also negative points. First of all, the optimal policy P star of n may not converge. So we may have cases where pi star, the optimal policy, does not converge, even though we know that A star is asymptotically optimal. It may not be optimal for any n. And finally, computing A star, solving the deterministic problem may be difficult, because in most cases, solving this deterministic system comes back to a HDB equation, and these equations are usually hard to solve. But I will show examples where this approach is very fruitful. I will skip this maybe. These are rates at which the convergence happens. Basically, just to say a word about it, when your system is Lipschitz, then you have convergence of the finite system to its fluid limit at rate 1/√n. And now let's try to put this in practice. So of course, in a general case, solving the HDB equation is not easy, but in some cases we can actually do it. And I will show you examples where we can do it. And the first one is an interesting one, because maybe it's related to a virus spreading in a population. So here actually I have looked at the case where the virus itself has a control of its behavior, but we have also looked at the case where instead of putting control into the virus, we put control into the people that get infected, where they and the policy there would be optimal vaccination policy. But here I look at the intelligent virus that actually may act, may have some control. So it's a dual case, if you want. So let me explain how it works. So you have many nodes. Okay, let's say it's maybe let's say like a computer system, and the nodes may be either susceptible. So S is a susceptible node, which is not contaminated by the worm, but prone to infection. So the nodes that have never seen the worm, but the worm may infect them, the virus. A node is infective I if it is contaminated by the worm. So the worm has already infected the node. It has taken control of that node. And of course, an infective node may spread the virus to other nodes around it with probability beta. Now, the action of the worm, this is what the worm can do. The worm, it can either kill an infective node and render it completely dysfunctional, or keep it alive. So that's the control that the virus has over its infected node. So whenever a node is infected, the virus may either kill it or keep it alive. I mean, there is a compromise. If it kills it, you get a big reward. But if it keeps it alive, it has a chance that this node will actually spread the virus to its neighbors. And so that's the optimal control for the worm. So here, this is the gain that the worm gets over the system. So D of NT here is the number of dead nodes at time NT, the final time. And you add to this some function of, you have some gain by having infected some nodes. So G is some convex function that tells you how much you gain per infected node. And this is the deterministic dynamics of the system. So it's very close to what is called the SIR dynamics. So here, for example, you look at what happens for the susceptible nodes. So susceptible nodes, they decrease at rate beta, which is the infection ratio times I times S, which is the infected nodes that meet susceptible nodes, minus QS. QS is the recovery rate, because you have also some recovery way. You can patch the virus out, and so that's QS. Now the number of infected nodes, you know, of course, it grows at rate beta IS. of course, they can also recover by themselves at rate B. And then here, alpha T of I is the action of the worm that decides either to kill or not to kill an infected node. So this is actually the differential equation, and the only control that we have on this equation is alpha of t that decides either to kill or not to kill at time t some infected nodes. And actually, in that case, when G is convex, you can actually more or less solve this optimization equation, and you can prove that the optimal alpha actually is a bank type. So up to some time T1, you never kill anybody. And once T1 is reached close to T, you start killing everybody with maximal rate. So you never kill for some time. And after some threshold time, you kill at maximal rate. And this is the optimal action for the worm. And actually, you can actually see what happens over some expected cases. So let me explain this curve. So here I plot, maybe look directly at the right curve because it's a zoom of the, of that curve that doesn't show much because everything is so close to each other. So let's directly look at the right curve. So here, the actually black line is the limit system. So this is the optimal value for the limit system when n equals infinity, V star. V star when you apply the optimal alpha star. And when n grows to infinity, the blue line here is the optimal expected value with n finite. So when n is finite, actually the cost is larger than the system, and you can actually compute the optimal value here. We computed it by solving the MDP. So that's the blue line here. And the red line is what you do, is what you get if you apply alpha star, the policy that optimizes the deterministic system, to the stochastic system. And you see that in that case, of course, you get a lower performance than the blue line, but you have convergence to the same value when n goes to infinity. And when you look at non-scaled case here on the left, you see that the blue and the red lines are very close to each other. So solving the deterministic case and applying in the stochastic one gives you a very, very good performance. This is another example that I wanted to show about brokering in parallel queues. So in that case, you want to decide where to send packets over processors, and so you have this is the following framework. So you have P applications that are sending tasks to some broker, and the applications may be either on or off at any point in time. So now you have C clusters of processors, and a cluster is given by a common buffer. So you have only one buffer per cluster, and you have K processors per cluster that can actually serve the application sent by the broker. And again, they can be either on or off. And the goal of the broker is, of course, to allocate the tasks to the clusters to minimize the average response time. In that case, the number of objects n is P plus CK, total number of processors, total number of applications sending tasks. And this is what happens. So we can actually, in that case, we can also solve for the deterministic system. And A star is a policy for the deterministic system, which is actually the solution of some water filling process. And here are the performances. So it's interesting to see them because we compare a heuristic A with smart policies. For example, we compare with GSQ, John the shortest queue, or weighted GSQ, where you send the packets to the queue with the smallest expected waiting time. And you see the performance of GSQ and weighted GSQ are given here. So this is GSQ, and this is weighted GSQ, and you see that asymptotically, when n goes to infinity, those two policies are not optimal. It's not optimal to use GSQ, John the shortest Q. However, our strange, very simple open loop policy A star, its performance converges to the optimal performance when n goes to infinity. So here for n equals 10,000, we have a clear difference between the performance of our simple policy and the dynamic ones, JSQ or weighted JSQ. Furthermore, as soon as n equals 50, A star, as soon as n equals 20, A star becomes better than any of the heuristics that look reasonable, like GSQ and weighted GSQ. Finally, this is the speed of convergence. So we look at the speed of convergence of the policy pi star and A star to the optimal value V star. And you see that when you plot the square root of the difference, then the square root converges to a finite non-zero value, which means that the actual speed of convergence of Vn to V star is exactly square root of n. So this is the best you can hope for. In that case, convergence happens at rate square root of n. So this is the last slide of my talk, and here I wanted to present you a little more material that is not covered by this talk. So in this talk, I only talked about the convergence in finite time. And you may also look at what happens with an infinite horizon. So when you let the time t go to infinity, and here you hit the problem of commuting the limits with n and t. So whether do the limits commute? Can you exchange the limits in time and in the number of objects? And the answer is actually no. In most cases, you cannot exchange the limits unless you have some very strong properties on your dynamical system, on your deterministic system. So, for example, you need that, that there is a C missing here. There is a typo here. It's missing a C. So we need that the deterministic system as a global attractor over the whole space to have convergence in most cases. Rate of convergence, as I said, the rate of convergence is in the square root of n, but actually, in most cases, we can show that it can be improved to 1 over n as soon as the drift has a Lipschitz property and is differentiable. There are cases where you have even a better rate of convergence in the exponential fast rate of convergence for some classes of MDPs, and in particular, this is the case for multi-armed bandits. This is a recent work we did. We looked at the multi-armed bandit problem, and we proved that in that case, when the number of bandits goes to infinity, the mean field limit approximation becomes closer and closer to the optimal at rate e to the minus cn, where c is a constant. Mean field techniques can also be used to compute the stopping time of randomized algorithms. So this is a work we did a few years ago, and especially we looked at the coupon collector as an example. So you may know about the coupon collector problem. So the coupon collector is when you have n coupons that you have to collect. When n goes to infinity, and you know that the expected time you have to wait before you collect them all is in n log n. But then you wonder what happens if you want the 2 samples of each coupon and maybe k samples of each coupon. And this is a much harder problems. These are much harder problems, and we can actually solve them easily using these mean field techniques. And finally, optimization results can be generalized to mean field games with a discrete or finite number of states under very minimal assumptions, as I said before.